So what we're going to look at now is a particular case where limits don't exist. So in all of the examples we're going to be looking at, the limit is not going to exist, but we can describe a little better how that limit doesn't exist. So let's look at this function right here, the graph of 1 over x squared. Hopefully somewhere somebody showed this to you once. Okay, you should be able to come up with its graph given just a little bit of time. Okay, if I plug in a 1 into this function, it spits out a 1, right? So it goes to the order pair 1, 1. And if I plug in a negative 1, it also spits out a 1, correct? Now, as I plug in large numbers for x, like 10 or 100, 1 divided by 10 squared, or 1 divided by 100 squared, these numbers tend towards 0. Okay? So away from 1, these numbers tend asymptotically towards 0. And away from negative 1, they tend asymptotically towards 0. What if I plug in small numbers? Well, 1 divided by a small number squared is a what? A big number, right? So if I did, for example, 0.1 and squared it, I'd have 0.01. And 1 divided by 0.01 is 10. Is it? 0.01 is 100. Okay? It's getting big real fast. Okay? So, in fact, this is what this function looks like as we approach 0. Does the limit exist as we approach 0? Are we approaching some fixed y value as we get closer and closer to 0? No. So the limit does not exist. And this is an important takeaway point, that the limit as x approaches 0 of f of x does not exist. But we'd still like to describe what's happening. Okay? We'd still like to describe what's happening. What I'd like to say is the limit as x approaches 0, in fact, let's say it like this. I want to say as x approaches 0, f of x gets large. I'd like to say that. Is that true? I mean, it appears to be true from this graph, right? So that's the idea that I want to convey, but I want to be able to give a symbol for that. So how are we going to write this? The limit as x approaches 0 of f of x, and I'm going to write equals infinity. And I want to say that this is a misleading idea. We're going to denote it this way. This is how all math people are going to write it, but it's a little bit misleading. Because does this limit exist? No. Is infinity a range value that you ever get to? It's not on the y-axis. Okay, so this is a misleading idea. But it conveys this sentence right here, which is very similar to the sentences that we were conveying in section 2.2 when we came up with this limit notation. So that's why we write it using the same notation. Okay? So the way I want you to think about it is when you see something like this, as x approaches 0, as my domain values get close to 0, what do my y values do? They get arbitrarily large. Okay? And so, in fact, let me just insert that word, arbitrarily large. Because what is large, right? Is a mile large? Right? But arbitrarily large, regardless of context, this gets large. Okay? All right. So we're just going to summarize that. Let f of x be defined on some open interval containing a except for possibly a itself. Then if the values of f become arbitrarily large, as x gets closer and closer to a, we write that expression there. The limit as x approaches a of f of x equals infinity. Likewise, if at the f of x values, the range values become arbitrarily, and here I'm not really sure how I want to say this, I'll say large negative. Meaning they're negative, and then in the absolute value sense, they keep getting bigger and bigger. Okay? Then we would write the limit as x approaches a of f of x equals minus infinity. Okay, so this is going to extend to right and left-hand limits as well. Okay, so if I want to approach just from the right, I'd put a plus sign there. If I want to approach from the left, I'd put a minus sign there, just like we did in previous questions. Okay? So one thing I just want to make sure you're taking away from this, we're still claiming that the limit doesn't exist, but we're doing a better job of describing how the function's behaving at that point, at that x coordinate. Okay? All right. If the left, right, or limit proper comes out to be plus or minus infinity, then we will say the graph of f has a vertical asymptote at x equals a. So we sort of, I mean, you encounter asymptotes early on in like an Algebra 2 course. You see asymptotes, but you don't usually get limits until later on. Okay? But really, an asymptote is a vertical asymptote is defined to be a situation where as we approach a particular domain or a particular x value, the limit came out to be either plus or minus infinity. When that happens, we say that there's a vertical asymptote there. But graphically, we've already learned what vertical asymptotes look like. Okay? Graphically, you've encountered enough of these to say, oh yeah, I see there's a vertical asymptote here at x equals 0. But what justifies that? The fact that either the left, right, or limit proper came out to be, is written as infinity, arbitrarily large. All right, working with limits where the output becomes arbitrarily large positive or arbitrarily large negative is difficult to do. We will prove one of them in section 2.7 with what's called the epsilon, with the epsilon definition of a limit. Okay? But it's an extremely complicated, well, I shouldn't say extremely, it's a chore. Okay? So I'm going to give you some facts that you can take from here on out. Now, these facts are true as I give them to you, but what happens is people start applying them in contexts where they don't apply. Okay? So all of the ideas that I'm going to give here in 7, which will be your takeaway point for this section, come from these unproven facts that I'm going to show you here. If you ever have any confusion about what's going on with 7, return to these unproven facts. Okay? Because you can't go wrong looking at this, where sometimes I've seen students kind of back themselves into a corner misusing these statements here. Okay? So, an unproven fact. If we look at the limit as x approaches 0 from the right of the function 1 over x, this limit comes out to be positive infinity. Now, I'm saying the limit comes out to be positive infinity. That's sort of poor vocabulary. What I'm saying is, as the domain values get close to 0 from the right, what do the range values do? They get arbitrarily large. Okay? So we get sloppy as we talk about it. We say the limit is infinity. But what we really mean is the range values are doing what? Getting large. Okay? So the domain value that we're approaching is 0. The range values are getting arbitrarily large. Similarly, if we look at the limit as x approaches 0 from the left of 1 over x, this equals minus infinity. Okay. I'm going to do something a little dangerous here. Okay. An arbitrarily, let me write it out. An arbitrarily large number times an arbitrarily large number is what? Another arbitrarily large number. Okay? For that reason, this is a fact that is really just summarizing what I put above it. Okay. Yes?
Why is it negative infinity?
That's a, I'm sorry, where? For this one here?
Yep.
Great question. Great question. Let's look at that. What does the graph of 1 over x look like? So the graph of this function looks like this. It's the reciprocal function. Yeah, thank you. I was going to put this picture up and I forgot. So thank you. Let's look at this function. As we approach 0 from the right, okay, remember, always when we talk about approach, that's the domain values. As the domain values get closer to 0 from the right, what are the range values doing? They're becoming arbitrarily large. But to Kasha's question, as we approach 0 from the left, as our domain values get inch closer and closer to 0, what are the range values doing? They're becoming arbitrarily large negative. So we write that it's minus infinity. How's that?
Okay.
Great. The next one I want to put is that if I take an arbitrarily large positive times an arbitrarily large negative, what will I get? An arbitrarily large negative number. Okay. Now, I just put up these two facts, and they are true. There is never an instance where that will steer you wrong. Okay? Be very careful. Later on, I've got a handout called Indeterminate Forms that we'll go over next time. Okay? This expression right here, an arbitrarily large number times 0, can't be generalized. You cannot say, when you take a large number times 0, you cannot generalize what that will be.
Why?
Great question. We will see that in some instances, if you take a arbitrarily large number times something that is approaching 0, you'll get 0. And in other instances, when you take an arbitrarily large number times 0, you'll get something that's arbitrarily large. And sometimes you'll get any number in between those. So it can't be generalized. It's what's called, yeah, the word for this is an indeterminate form. This structure can't be generalized. It's indeterminate. Think about that word indeterminate. You can't just look at that structure and say, I know what that's going to come out to be. Okay? And we'll look at a handful of examples in that form next time. But basically, when you do something like this, all your intuition goes out the window. You can't rely on your intuition for something like that. Okay? You have to look at the specifics of the functions that you're dealing with. And you can't make generalizations about it. Yeah, it's a really good question. And it's what a lot of calculus is about. We're kind of narrowing in on the issue here. Okay? All right. So, this first statement here, though, is the one that I say, if you have trouble remembering these facts, return to this. Because if you return to this, combine it with this, you can sort of talk yourself through any of these other problems. Okay? For these section 2.4 questions, you usually don't need to show me any work, because you just fall back on this unproven fact. So there's no real work to show for them. Okay? So, what are these two ideas? A positive quantity that does not approach 0 divided by a arbitrarily small positive number approaches infinity. Okay, think about that for a second. If I take the number, I don't know, if I take the number 23, if I take the number 23 and divide it by 0.1, what do I get? 230. If I take the number 23 and divide it by 0.01, what do I get? 230. 2,300. If I take the number 23 and divide it by 0.00001, I get a very large positive number. The closer this expression gets to 0, the more large the quotient becomes, so we're approaching infinity. Now, the thing that is critical here is this might be 23.1, and this might be 23.01, and this might be 23.001 as you're evaluating limits, looking at the overall structure of it, but it's approaching a positive number. Specifically, it's not approaching 0. Okay? If both of these are approaching 0, these statements in 7 don't apply. Okay? That's really, really important. All right. Same thing. If a positive quantity that does not approach 0 is divided by an arbitrarily small negative number, then the whole quantity, the quotient, approaches negative infinity. Okay. Okay, so let's go ahead and we're going to analyze limits to determine where vertical asymptotes are. And I'll say this once. We'll go into more detail in the next section next time on Wednesday's class. But let me just say, vertical asymptotes and holes arise from exclusions in the domain. So whenever you're looking for either vertical asymptotes or holes, you say, where are the boundaries of the domain of this function? And let's go explore those. This function's not defined where? At 3. So at 3, we will either have a vertical asymptote or a hole or both. We will see one example of a function that has both a vertical asymptote and a hole at the same location. That'll be kind of interesting. You may not have seen one of those before. So, what's happening at x equals 3? I don't know. Let's go find out. Okay? So, we're going to look at the limit as x approaches 3 of 2x over x minus 3. We're going to approach the problem in the domain. We can't plug in 3. Why? This function's not defined there. We're going to explore the area around that problem. But here's the thing. I'm trying to use my number 7 shortcut stuff on the previous page, and I can't do it because I can't generalize what's happening as x is approaching 3. So let's pick a direction of approach first. So let's approach it from the right. Okay? What is the numerator of this expression approaching? 6. The numerator is approaching 6. What's the denominator approaching? A very, very small but positive number. What is a positive number divided by an arbitrarily small positive number? You can use without any justification. You can say that equals plus infinity, or just infinity. Okay, please put an equal sign there. Some people were putting equal signs in my last class. Okay. What if we go the other way? We look at the limit as x approaches 3 from the left of 2x over x minus 3. Well, even though I'm approaching 3 from the left, I'm plugging in numbers like 2.9 or 2.99. What happens when I multiply that by 2? I get numbers that get close to what again in the numerator? 6. Divided by a very, very small but negative number. Positive quantity divided by an arbitrarily small negative number, no work is required, is negative infinity. Okay? I want to make something very clear here, folks. I've talked through the explanation of this in the air. If you wanted to give yourself some notes, you could do something like this. Draw an arrow and say that you got this because you had 6 over a small positive. But the thing that I don't want to have happen is I don't want this expression to show up equaling the math that you're doing. This is just the in-the-air justification that I'm giving for this problem that requires no work. Okay? Because it bothers me when people start writing 6 divided by 0.001 equals infinity. Well, it doesn't equal infinity. You can do 6 divided by 0.001. That equals, 6,000. Okay? So this is just the scratch work off to the side that's justifying this true statement here. Okay? All right. By the way, we don't have to say this, but what is the limit proper? Does not exist because the left-hand limit and the right-hand limit weren't equal. Okay. Now, what was the question? The question didn't ask us to compute limits. We had to compute them to answer the question. What was the question here? Yeah, where are the vertical asymptotes? Well, what did we find? We found when we explored this area, one or both or all of these limits came out to be infinity. So we have a vertical asymptote at x equals 3. Folks, don't just say there's an asymptote at 3. Please give me x equals 3 so I know that you know you're talking about a vertical line, not a horizontal one. Okay? So don't just say there's a vertical asymptote at 3. Say at x equals 3. I had very few happy faces in my morning class after this lecture. It's all right. You guys are a more jovial bunch, right? We're having fun, right? Yeah. All right. Similar problem. Okay. I'm going to go ahead and look at the limit as x approaches 3 from the right, and I'll go ahead and it doesn't matter where I put this. I'm going to move the negative sign up there. It'll just be a little bit easier to talk about as we do this problem. Okay. Negative 2x over x minus 3 quantity squared. Okay. So, folks, this one up here, 8a, is the stereotypical, the quintessential example. Okay? I feel like you can learn it all from this one idea. So now I'm just taking the idea and extending it. All the rest of these are extensions. They're a little bit harder than this first one. Okay? In this case, what's my numerator approaching? Negative 6. So if the numerator is negative, you just invert these properties that we talked about. Okay? So the numerator is approaching negative 6. The denominator is approaching an arbitrarily small what? Positive number. Why? Because I'm plugging in numbers like 3.1, 3.1 minus 3. That's positive. So a fixed negative number divided by something that's arbitrarily small and positive is going to come out to be no hands, no work required, no justification from you, negative infinity. Okay. All of that boils down to some extension of 6 and 7 here. All right, let's look at the limit as x approaches 3 from the left of minus 2x over x minus 3 quantity squared. What's this one? Take a minute and talk yourself through it. Go. Everyone work through it. Some of you are right, some of you are wrong. What's the numerator approaching? What's the denominator approaching? Is it negative? When I plug in 2.9 and subtract 3, I get negative. But then what do? Square it, which makes it positive. So we still have a negative over an arbitrarily small positive. So this is still minus infinity. Be careful, folks. Be careful. You have all the tools you need. You just need to learn to be careful. What I would recommend doing is always returning to the first example. Whenever you get lost with these problems, return to the first example to get your bearings again. And then go tackle the harder ones. Okay? Is there a question? Any questions on that? How do we feel about that? Give me a thumbs up. I mean, it was a little confusing at first. Thumbs up, thumbs down, thumbs sideways. Okay? All right. This one for the transcendental functions, sines and logarithms, and exponentials, you can use your knowledge of their graphs to answer the questions, and that's what I would do. Okay? What does the graph of the natural log of x look like? I hope you remember. If not, there's a video. I just put it up there today, brand new video. You'll be the first to watch it if you get online quick after class. Okay? So I'm not going to explain it. There's the graph of the natural log function. Of course, it passes through the order pair 1, 0. Why? Ooh, better watch the video. Okay? So let's look at the limit as x approaches 0 of the natural log of x. Right? That's the boundary. What's the domain of the natural log function? Its domain goes from 0 to infinity. So what's the boundary of its domain? 0. Let's explore it. Wait a minute. What's the boundary? 0. Can I approach 0 from either direction? No, because I can only take domain values from where? From the right. It only makes sense to do domain values from the right. Does that make sense? Yeah.
I'm just confused on that last one.
Yeah, so the domain is only for positive numbers, and for limits, we can only plug in values in the domain that are getting close to the value that we're taking the limit at. So I can't plug in numbers like, I can plug in numbers like 0.5 or 0.12 or 0.003, but I can't plug in numbers like negative 0.5 to explore how the function's behaving near 0, not because of a limit issue, but because it's not even in the domain to begin with.
Oh, never mind. Oh, I see.
That's all right. That's right. Yeah, I appreciate the questions. Okay. All right. This I said you can just do from the graph. What's the answer? Negative infinity. You never have to, for these problems, you never have to justify to me why the answer is infinity or negative infinity. Because there's only one way to justify it, and it's a rigorous proof. And we will do that once in 2.7 and say that's for other folks to do. Okay? All right. Let's look at this one. Okay. So I want to look at the limit. Where's the potential vertical asymptote at?
3.
Potentially at 3. So let's approach 3. But what's the issue, folks? Can I approach 3 recklessly? No. Can I plug in numbers like 3.1 for x? Can I plug in numbers like 3.5 for x? No. What's the domain of k? The domain of k, this is, we had domain quiz. This problem was almost on it, almost identical. What's the domain of k? Minus infinity to 3. What goes on the end there?
Square bracket.
It's a parentheses.
Oh.
It's a square bracket if the radical was in the numerator, but because the radical's in the denominator, I can't have an output of 0 from taking the square root, which means I can't take the square root of 0, which means x can't be 3. We okay with that? Anyone want to talk about that more? Well, guess what? You got a chance to redo those domain quizzes, and you'll get to go through that again. Okay? All right. So can I just approach 3 from any direction? No, I've got to approach it from which way? From the left. Folks, calculus boils down to limits. Limits boil down to having a kind of an understanding. I shouldn't say they boil down, but it sure helps to have an understanding of these functions, which includes understanding their domain. Tough stuff. This is not easy. This is not easy. This is tough stuff. Okay? Had a few people during office hours. I'm really excited. So come join us. Right? We're all lost, but we're all figuring it out in there. So come on by and see me during office hours. Go to the Math Center right before this class, 4 to 6. Trevor's there. Trevor's a very clever fellow. He'll help you out. Okay? 4 to 6, Mondays and Wednesdays. He's there. Twiddling his thumbs, I'll bet. saying, geez, I'm getting paid just to sit here and nobody's asking me questions. So you got lots of options for getting help. All right, back to this. Okay? I'm just going to run through the same analysis as before. Okay? We've got 1 over, so we've got a fixed positive. When I plug in numbers like 2.9, I've got a small positive number. When I take the square root of a small positive number, it actually gets a little bigger, but it's still small and still positive. So we've got 1 over an arbitrarily small but positive number, so we are approaching positive infinity. Okay? No justification required there. Yes?
So with like square roots, how you can like the square root of 9, it can be like plus or minus 3, or just gonna be...
No, so careful with that. It's a good question. If I say solve for x, the equation x squared equals 9, and you want to isolate x, you could apply the square root method. And when you apply the square root method, instead of factoring this, you say x is equal to plus or minus the square root of 9. That was me applying the square root method, which is actually shorthand for me saying what's x squared minus 9 equal to 0. That factors to be x minus 3, x plus 3 equals 0, which gives me the two answers, x equals plus or minus 3, which is what this would give me. But that was a procedure where I was using the square root method. If I just give you a square root, solve for x, I don't know, let's say this, 9 equals the square root of x. I don't put a plus or minus there. I'm just working with the square root. Yeah, so the phrase some people like to use is whenever you induce the radical, you need to put a plus or minus there. Okay? But this problem it was just a radical to begin with. You didn't put the radical there. Good questions, folks. Okay, I'm getting the hang of this. Wherever the function's undefined, I've got a vertical asymptote. Is that always true? No, because of the inflection in his voice, it can't be. Right? That's correct. Okay, let's look at this one. Does this have any vertical asymptotes? I don't know. What should we do? Well, we should go look at the behavior near 1. I'm going to go ahead and keep the limit proper until I feel like maybe I'll have to break it down, but I don't think I will in this case. Somebody said, hey, this sounds a little familiar. Let's factor the numerator. We get down to a place where we can do apply the direct substitution. What did this limit not come out to be? It didn't come out to be plus or minus infinity. Do we have a vertical asymptote at 2? Or at x equals 1? No. The limit proper didn't come out to be infinity. The limit proper came out to be 2. So what are the left and right hand limits? They're also 2, right? If the limit proper is something, then the left and right hand limits have to agree, correct? So they're also 2, so they're not infinity either. So there are no vertical asymptotes. In fact, what do we have at x equals 1? At x equals 1, f has a hole. Okay. Okay. If f is undefined, I should have put at x equals a, but the limit as we approach a exists, then the graph of f has a hole at x equals a and not a vertical asymptote. That's the best generalization I can give you. Anything else would be a lie at some point. Okay? So if the function's not defined there, but the limit proper exists, then you've got a hole there. Okay? That's the best you can do as a generalization. Warning, if the limit does not exist, that does not necessarily mean that f has a vertical asymptote there. We've seen lots of examples of that. So for example, we had this one last time, the graph of this function. This was the graph of f of x equaling the absolute value of x minus 3 over x minus 3. Does the limit exist at 3? No. How come? The left and right hand limits don't agree with each other. Do I have a vertical asymptote at 3? No. So anyway, in fact I have holes there, but they're kind of left hole and right hole. Anyway. Okay, I'd like you to now take some time, work numbers 11 as in either pairs or in your groups. So you decide if you'd rather work in pairs or groups of 3, great. If you'd rather work as a whole table, that's fine. But work with somebody. You must be working with at least one other person. Okay? And work through number 11. Don't move on to 12 until everybody in your group, your little subgroup, agrees. Then move on to 12. Once you get done with those, move on to 13. Okay? 13 is the meat and potatoes of this thing. This is where you show me that you understand what's going on. Okay? But work through 11 and 12 first. Make sure everyone agrees. Make sure you write your vertical asymptotes as x equals a number, not just 3 or 7 or something like that. Okay? All right. Take a few minutes, work through that. We're left with the limit as x approaches negative 3 from the right of x minus 3. But this limit can just be about, once we've cleaned up the thing that's preventing us from direct substitution, let's use direct substitution. And so we end up with minus 3, or negative 6. Okay? So that's just a warning. Not all problems are going to be like the ones in this section. Okay? All right. So let's look at what's going on here. This is going to be equal to minus infinity. What's the argument that we make? Well, what's the numerator approaching? Negative 1. Is that approaching 0? No, so we can just make note of its sign. Okay, the numerator is approaching negative 1. The denominator is approaching 0, but how? It's going to be very small, but what? Yeah. What's a number to the right of negative 3? No? Negative 2.9. Okay? Folks, I did the negatives on purpose. There's 0. There's negative 3. What's a number to the right of negative 3? A number like negative 2.9. Now add 3 to it, you get a very small but positive number. Negative 1 divided by an arbitrarily small positive number is negative infinity. There was a lot of talking involved in that problem that involves no work for you to show me. Okay? If you wanted to write something down for your own benefit, you could write negative 1 over a small positive. Notice where I wrote this expression. It's just scratch work pointing at my answer. It is not in line. This is not an algebraic step that I did to get at the answer. This is just sort of a behind-the-scenes justification. There is only one way to show that this answer is truly negative infinity, and it's a messy proof. So we're not going to do it. So I'm giving you a sloppy way of getting there, but just because I'm saying, hey, you can jump to the answer without any work doesn't allow you to give me incorrect work. Okay? All right. So by the same argument, then, this is infinity. Any questions on that? Okay. What is the limit proper, then? Doesn't exist. For the limit proper to exist, both the left and right hand limits either both exist and agree with each other, or they're both positive infinity, or they're both minus infinity. Okay, so adding to that definition a little bit. But basically you could say, hey, these two things don't agree with each other, so it doesn't exist. All right? Folks, you'll get to work with problems like, what's the domain of this function? You'll get to work with problems like that in the domain quiz. Okay. What is the domain of this function? No? How did I come up with that? Oh, see the quiz. See the video. Okay. see the quiz. Let's see the video first and then take the quiz. It'll help to explain it. But does that make sense? I mean, let's see here. If I plug in a -4 and square it, what do I get? 16. 16 minus 9 is 7. Can I take the natural log of 7? Oh boy. Yes, you can. Okay? All right. So that's the domain of this function. So it makes sense that I asked you to approach 3 from the which way? From the right. The question would be nonsensical. You'd say the limit didn't exist if I asked you to approach 3 from the left, because it's not even in the domain. Okay? So then you can run through sort of the same line of argumentation, provided you remember what the graph of the natural log looks like. The graph of the natural log looks like this. Somebody should be able to wake you up from the deepest sleep, shake you awake and say, draw a natural log of x. And you should be able to do it. I'm going to say, now let me go back to sleep, but you should be able to do it. Okay? You have to know it that well in this class. Okay? There should be no time required. When I say natural log of x, that picture should come into your head. So put it on a flashcard. Make flashcards. I think that's helpful. Okay? So when I plug in something a little bit bigger than 3 and square it, what do I get? Something a little bit bigger than 9, correct? Like if I take 3.1 and square it, I get 9.01, I think. Okay? But then I subtract 9 from it, what am I left with? A very, very small but positive number. And what is the natural log of very small but positive number? Well, we look at the graph. And the graph says, as this gets closer and closer to 0 from the right, our y values are getting closer and closer to minus infinity. Okay? By the way, the graph of this function is kind of interesting. Let me put it up on the board for you, just for your benefit. Okay, what does the graph of this function look like? It looks like this. 1, 2, 3. 1, 2, 3. Here's 4. Passes through 4. Here's -4. Passes through -4. So we can see as we approach the graph of this function, we approach 3 from the right, we're approaching negative infinity. What if you couldn't graph that? Let me do one more thing. I'll put it on the video for your somebody. Okay. Here's another way to analyze this limit. Okay. If you don't understand it today, that's fine. You have until Wednesday to figure it out. Okay. Wednesday I'll teach you one more time. Okay. The limit as x approaches 3 from the right of the natural log of x squared minus 9. What I'm going to do is something called a u substitution. Okay? And it's worth, we do this technique over and over again in this class, so I might as well start seeing it now. Let's let u equal x squared minus 9. How does that help me? Well, now I'm going to take the limit of the natural log of u, which I know all about the graph of the natural log of u. So it's a lot easier. So if I couldn't see this graph, I couldn't come up with this graph, I do know the natural log of u, or I expect you to know it. Okay. Here's the graph of the natural log of u. Okay. Now, this is the rub, though. This is the hard part about doing a u substitution. You've got to adjust all elements in the u substitution. Our limiting variable here is x. What is our limiting variable here? U. What will u approach? Well, let's find out. As x approaches 3 from the right, what is u approaching? No?
0.
So what is u? It's x squared minus 9. So x is getting closer and closer to 3. So u is getting closer and closer to 0 from the right. So this is a way to more formally do what we talked through originally. Okay? So we're approaching 0 from the right. This is now a question, just like the original question. What's the graph of the natural log of u look like? It looks like that. As we approach 0 from the right, we're approaching minus infinity. Okay? So that's a more... For those of you that didn't like my kind of talking through the air explanation, here's a more rigorous way of showing that the limit is, I don't know if rigorous is quite right, but here's a little bit more justified way of explaining why that limit's minus infinity. Tough stuff, folks. This is tough stuff. I usually do this unit 1 day shorter, but I figured since you were a summer class and this was going so fast, we have 1 extra day for our unit. Usually I do it a day faster. Extra work now definitely pays off down the road. Okay? Extra work now pays off big time down the road. Okay? Getting lost now compounds. So if I've lost you, never fear, right? We got a long time to get this straightened out. But what can you not do? You can't go home and say, well, it'll make sense next time I look at it. Because it won't. Okay? You got to start tackling it. Start with what you do know. If you figure out how to answer a question, that's a victory. Put that on a piece of paper. Refer back to it. Redo that exact same question that you've mastered. Okay? That way, when I do a slight deviation from it, you're able to handle that change. Okay? All right. I think let's see. Well, I guess we better finish this out. Okay. 2 ways to handle this one. Two ways to handle this one. Okay. One is to say, aha, somebody told me I better memorize the graphs of all my trig functions, so I did. Okay. What does the graph of the cotangent curve look like? It's got asymptotes at all the odd multiples of pi. Oops, that's not true. It has asymptotes at all the multiples of pi. Where the tan curve rose up like this, the cotangent curve dies down like this. You have the curve memorized and asking the question, how does it behave as we approach pi from the left? It's easy to see that the answer is minus infinity. Okay, again, for these ones, when the answer comes out to plus infinity or minus infinity, I need no justification for it. Okay. So if you look at the graph, that's perfectly fine with me. Okay. Here's another way to tackle the problem, though. We could look at the limit as x approaches pi from the left of, let's go ahead and rewrite the cotangent as the cosine of x over the sine of x. That's not going to solve all of our problems. Okay. But we can now analyze this one sort of like how we were with the earlier problems with that rule 7. Okay. What is the numerator approaching? Yeah, what's the cosine of pi? Altogether, cosine of pi is -1. Make a note, go home and learn that. Okay. Cosine of pi is -1. Okay. This one's a little bit harder. Sine of pi is what? 0, but the direction of approach matters here. So even though, you know, if you can't pull up the curve of the cotangent, you still have to know the curves of some of the trig functions to answer this question. This is at pi over 2. This is right here at pi. What is the sine? What is the sine on the sine as we approach pi from the left? The y values as we approach pi from the left are positive. So what have we got? We've got -1 over a very, very small but positive number, so it's negative infinity. Okay? So again, notice what I didn't do. I didn't, in the middle of writing my equations, I didn't write that this was -1 over a small positive quantity, but that's sort of the justification that we talked through in the error.